Hello. So in the last class, we actually discussed uh, the effect of varying spatial resolution and also the brightness resolution. And we also looked into the concept of image zooming and image shrinking. So in this class, let us just try to solve a problem on how we can zoom an image by using interpolation technique. So uh, as we discussed in the last class, zooming is actually viewed as oversampling and shrinking as undersampling. And zooming and shrinking are applied to digital images. And we also discussed in the previous class that it has two steps. You have to create the new pixel location and assign the gray level to these new location. And when you are assigning the gray level, either I had to use nearest neighborhood interpolation to calculate the new value or bilinear interpolation. Now, if you are doing image shrinking by a factor of an integer, then it is just row column deletion. And non-integer factor, then you should follow the same steps that you follow for image zooming. So let us take an example of a 2 cross 2 image, which has to be zoomed to a 4 cross 4 image. So uh, we have 4 pixels here, and we need to have 16 pixels here. Out of these 16 pixels, the corner pixels are same as the original pixels, as you can observe here. So now we need to calculate these values A, B, C, D, etc. And the first thing that you should do now is, as we saw in the previous discussion, I should first find the location of these points. So if you carefully observe, uh, over a distance of 1 unit, I should actually have three pixels here. So which means each of them, each of them will be at 1 by 3. So this distance will be 1 by 3. Similarly, this distance will also be 1 by 3. This will be at 1 by 3. So at every 1 by 3 position, you need to have a pixel. So now I know what is the distance of each of this new pixel value from the uh, values 1. So let us see how we can evaluate these values. Okay. So the situation now is I have the neighbors here. So let me just take this neighbor as A1, this neighbor as A2, and this is A3, and say this is A4. These are the four neighbors. And let us assume that I need to calculate a value V, which is at a distance X along this direction and Y along this direction. So what is required is you need to calculate V at XY. So once you locate these positions, once I know the value of X and Y, V of XY, the value will be calculated as follows. So the assignment of value, one method as we saw is nearest neighborhood interpolation. And nearest neighborhood interpolation, as you know, it just copies the nearest neighbor to the value to the position xy. So in our case here, as you can see, A is at a distance, A is at a distance 1 by 3 along y direction and 0 at along x direction. So, so you can easily say A is at a distance So if you carefully observe, A is close to 1, D is, that means A, C, D, all of them are close to 1. Therefore, I can say these values are 1, 1, 1, 1. And B, E, F, they are close to 2. Therefore, these values will be 2. Similarly, the other values. These are close to 3, 4. So this is how you can calculate the new values by using nearest neighborhood interpolation and obtain a zoomed image. Now let us just see how we can do it for bilinear interpolation. So bilinear interpolation is an improved version where you give weightage to all the neighbors, and the value v at x comma y is calculated using the following formula: a1 into 1 minus x into 1 minus y plus a2 into 1 minus x into y plus a3 into x into 1 minus y plus a4 into xy. So as you can see, the value is given, in fact, is calculated by giving weightage to all the values, all the neighbors a1, a2, a3 and a4. So we can further simplify this. 1 minus y minus x plus xy plus a2 into y minus xy plus a3 into x minus xy plus a4 into xy. I will further simplify this by taking only factors containing x. So it is a3 minus a1 into x. Factors containing y, a2 minus a1 into y. Factors containing xy, it will be a1 plus a4 minus a2 minus a3 into xy plus a1. So I can call this constant as a into x plus this constant is b plus the next constant is c plus this I'll just call it as d. So the value v at x comma y can be calculated by using this formula. So if you observe this, you can see the value at x comma y can be calculated as ax plus by plus cxy plus d, where a is a3 minus a1, b is a2 minus a1, c is a1 plus a4 minus a2 minus a3 plus d is a1. So a is a3 minus a1, b is a2 minus a1 and c is a1 plus a4 minus a3 minus a2 and d is equal to a1. So knowing the four neighbors, knowing the distance of the new pixel position, that is x and y, you can calculate the new value. So let us use this method to calculate the values a, b, c, d, e, etc. So I'll rewrite it again. So this is 1, this is 2, this is 3, and this is 4. This is A, this is B, C, D, etc. So here, as I already told you, this distance is 1 by 3, and so you can see for A, the value of x is 0. That means there is no shift along the x direction. The value of y is 1 by 3. Therefore, A is equal to A3 minus A1. A3 is 3, A1 is 1. So 3 minus 1 into x is 0, plus A2 minus A1. 2 minus 1. 2 minus 1 into y is 1 by 3. 1 by 3 plus A1 plus A4, that is 4 plus 1, 5. 4 plus 1 minus 3 minus 2 into 0 into 1 by 3 plus D is A1. A1 is 1. So I can calculate A as, this term is 0. So it is 0 plus 1 by 3 plus 1 plus 1 by 3 is 4 by 3. Similarly, to calculate B, you know the distance of B from 1. This distance is 2 by 3 and x is 0. So for B, x is equal to 0, y is equal to 2 by 3. So I can calculate this as 3 minus 1 is 2. So 2 into 0 plus 2 minus 1 is 1 into 2 by 3 plus the third term is anyway 0 plus 1. This is equal to 1 plus 2 by 3. 3. So this will be 1.67. This will be 1.33. Now, suppose if I need to calculate, say, D, if I want to calculate D, for D, x is equal to 1 by 3 and y is also equal to 1 by 3. So you can observe this distance is 1 by 3 and this distance is also 1 by 3. Therefore, D is 2 into 1 by 3 plus 1 into 1 by 3 plus third term is 0 plus 1. So this is equal to 2 by 3 plus 1 by 3 plus 1. This is equal to 2. So like this, you can calculate all the values and I will give you the final answer, which you can verify later. So this is 1, this is 2, this is 3 and 4. These are the original values. This will be 1.33, 1.67 and other values of this is 1.67. This value is 2. We have calculated this 2.33, 2.67. This value is 2.33, 2.67, 3.33, 3.33, 3.33, 3.67. So these are the new values. Now if you carefully observe, you can see that bilinear interpolated image is smooth in nature. So there is a gradual change from 1 to 2. As you can move along any direction, there is a gradual change. Whereas In nearest neighborhood interpolation, there is a sudden transition. So because of this, nearest neighborhood interpolation actually introduces the effect called checkerboard effect. So the observation is nearest neighborhood interpolation introduces checkerboard effect, and bilinear interpolation yields a smoother image. So this is the observation. So let me just demonstrate this by using a simple MATLAB command. So what I have done here is I have read a child image. I have reduced it to a size of 50%, and I have reduced this to a size of 25%. Now I just want to resize them. In fact, I want to resize the second image by 4 times using nearest neighborhood using bilinear, and let us see the effect. Okay, so notice here, this is by using nearest neighborhood interpolation, and this is by using bilinear interpolation. So you can easily see the checkerboard effect seen particularly near the edge portion, whereas the bilinear interpolated result is smoother. So this is how you can verify or compare the performance of nearest neighborhood interpolation with bilinear interpolation. So this is about image zooming using bilinear interpolation, and these are the results. So as you can see, the first row here is by using nearest neighborhood interpolation. This is by using a bilinear interpolation. You can notice the checkerboard effect, the smoother image here. This is a second example which uh, demonstrates the performance of the two interpolation techniques.